Module 12, Energy and Life. Introduction. Now that you know a little bit about the skeleton, muscles, and skin, I want to discuss something they all use, energy. The muscles use energy to contract and relax. The bones use energy to grow and make blood cells, and the skin uses energy to produce hair, skin cells, and nails. In fact, energy is used in all parts of our bodies. Indeed, energy is such an important component of life that it is central to our second criterion for life. All life forms have a method by which they extract energy from their surroundings and convert it into energy that sustains them. In this module and the next, I want to give you an introduction to how that happens in your body, as well as how it happens in many other organisms. Life's energy cycle. Before I start discussing the ways in which your body satisfies the second criterion for life, I want to spend some time on a few fundamental concepts. First, I want to ask you a very simple question. Where does all this energy come from? After all, the second criterion for life says that living organisms take energy from their surroundings and convert it into energy that sustains them. Well, if living organisms take energy from their surroundings, it must already be there waiting to be taken. Where does it come from? Almost all the energy used by living organisms comes from one place, the sun. There are some bacteria that get their energy from certain chemical reactions involving sulfur or methane, but most organisms in creation get their energy from the sun. Now that might sound a little strange to you. After all, you know that you get your energy from the food you eat and the liquids you drink. If you were to stop eating and drinking and simply lie out in the sun all day, you would die. You wouldn't be able to satisfy your energy needs that way. How then can I say that the energy in your body and the bodies of most organisms originated in the sun? Well, think about it. When light from the sun hits the earth, plants and other organisms like algae convert that energy into food for themselves. We call such organisms producers because they produce food for themselves. Producers, organisms that produce their own food. It's easy to see how the energy a producer uses comes from the sun. Through the process of photosynthesis, producers use energy from the sun, carbon dioxide, and water to make a sugar called glucose. That glucose is then used by the plant as food. The plant then converts the energy of the sun into glucose, and it uses the glucose as food for energy. That's not the end of the story, however. God has designed producers to make a lot more food than they need. They store this excess food usually in some chemical form other than glucose. Plants, for example, usually store their excess food as starch or fat, as in seeds. When animals eat those plants, they are using that starch or fat to produce their energy. Thus, even though these animals cannot get energy directly from the sun, they get it indirectly by eating the food that the producers made. We call such creatures consumers because they consume other organisms to get their food. Consumers, organisms that eat living producers and or other consumers for food. Human beings are consumers. We eat plants and we eat meat, which comes from animals. Those animals ate either plants or creatures that had eaten plants. In the end, then, the energy of life comes from the sun because the producers produce the food from the sun's energy, and the consumers eat the producers or they eat other consumers that have eaten the producers. There's actually a third group of organisms I have not mentioned yet. The decomposers you learned about in Module 10. Although you could classify such organisms as consumers, after all, they do not produce their own food, they are classified separately because they play a distinct role in creation. Decomposers recycle dead organisms. You see, as a decomposer eats a dead organism, the organism is broken down into chemicals that act as fertilizer for producers. Now remember, fertilizer is not plant food. However, fertilizer does act like vitamins that make plants healthier. As a result, producers use the products of the decomposers. This makes the decomposers different from the consumers. Now I need to make a very important point. Not all organisms that eat dead things are decomposers. Vultures, for example, eat dead animals. However, the process of a vulture eating a dead animal does not produce fertilizer for plants. Thus, a vulture is not a decomposer. As you will recall from experiment 10.2, yeast is a decomposer. That's because when yeast eats dead organisms, the organisms are broken down into substances used by producers. Throughout this discussion so far, I have classified organisms by whether they are producers, consumers, or decomposers. However, we can get a bit more detailed than that. If an organism is a consumer, it can be further classified. Remember, giraffes are consumers because they eat producers. Lions are also consumers, but they do not eat producers. They are consumers because they eat other consumers. Also, people are consumers because we eat both producers and consumers. If a consumer eats only producers, it is called an herbivore. Herbivore, a consumer that eats producers exclusively. If a consumer eats only other consumers, it is called a carnivore. Carnivore, a consumer that eats only other consumers. Finally, if a consumer eats both producers and other consumers, it is an omnivore. Omnivore, a consumer that eats both producers and other consumers. From these definitions, then, you can see that giraffes are herbivores, lions are carnivores, and humans are omnivores. The multimedia CD has a video about herbivores, carnivores, and omnivores. On Your Own 12.1. Classify each of the following as a consumer, producer, or decomposer. A. Grass. B. Horse. C. Tree. D. Yeast. E. Sparrow. F. Shark. 12.2. A creature's diet includes leaves, fruits, and certain bugs. Is this creature a carnivore, herbivore, or omnivore? If one of the three items from the list were removed, the creature would be classified differently. What one thing would have to be removed, and what would its new classification be? Now, before I leave this section, I want to bring up something I mentioned in passing before. While the vast majority of energy used by living things comes from the sun, some of it does come as a result of specific chemical reactions that do not need the energy of sunlight. One place you can find such chemical reactions in creation is at the bottom of the very deep parts of the ocean. In the deep ocean, sunlight cannot penetrate to the ocean floor. Nevertheless, you can find producers there. These producers live near fissures in the ocean's bottom, called hydrothermal vents. As you will learn in physical science, the interior of the Earth is very hot. Hydrothermal vents expose this hot interior. When a hydrothermal vent is at the bottom of the ocean, it spews forth superheated water that is rich in various chemicals, some of which can be used by bacteria to make their own food. Even though these bacteria do not use sunlight, we would still call them producers because they produce their own food. Well, what do you think the presence of producers at the bottom of the ocean causes? You guessed it, it causes the presence of consumers that are looking for a meal. Thus, hydrothermal vents at the bottom of the ocean support a rich community of producers and consumers, all of which take advantage of the energy stored in the chemicals that are spewed into the ocean. Because it is a relevant and enduring theme in the study of life, you also find examples of symbiosis in these communities, as shown in the figure below. How do organisms get energy from food? So now you know that producers make their own food, usually from the sun's energy, and consumers eat that food by eating producers or eating animals that have eaten producers. Also, you know that decomposers eat dead organisms and recycle those dead organisms back into creation. However, I still haven't told you how organisms actually get energy from food. Well, that's not an easy question to answer. In fact, I will spend the rest of this module and the next just giving you an introduction to how this is done. The process is quite fascinating and well worth the time it will take to discuss. In short, organisms get energy from food by burning their food. Now, don't get the wrong idea here. There aren't little fires going on in your body. Nevertheless, the chemical process by which organisms get energy from food is a combustion reaction. Combustion reactions are what occur when wood, paper, and other flammable materials are burned. Thus, much like we can get energy to heat our home by burning wood in a fireplace or natural gas in a furnace, organisms get the energy they need for life by burning their food. Of course, the burning process that goes on in organisms is quite different from the burning process that goes on in a fireplace or a furnace. Nevertheless, there are a few similarities. I want you to perform the following experiment to see some of those similarities. What did you see in the experiment? If everything went well in steps 1 through 3, you should have watched the flame on the candle slowly dim until it went out altogether. Why did that happen? The flame of a candle comes from the combustion of the wax that makes up the candle. Combustion requires oxygen. When you put the glass over the candle, the oxygen in the air surrounding the candle could not be replenished. Thus, when all the oxygen was used up, combustion could no longer occur, and the flame went out. The second part of the experiment demonstrates the same fact, but in a much more interesting way. You see, when baking soda and vinegar mix, a chemical reaction occurs. This chemical reaction produces carbon dioxide gas. That's what the bubbling was all about. The bubbles you saw were the result of carbon dioxide gas forming in the chemical reaction between baking soda and vinegar. Well, as the baking soda and vinegar produced carbon dioxide gas, the gas began to fill up the surrounding area. In other words, the carbon dioxide gas began filling up the bowl. To make room for itself, the carbon dioxide pushed away the air that was in the bowl. Eventually, then, there was no more air surrounding the candle, only carbon dioxide. As you will learn in physical science, air is a mixture of gases. One of the gases in that mixture is oxygen. Since the air was pushed out of the way by the carbon dioxide, the oxygen was pushed away along with it. Once most of the oxygen was pushed away from the candle, the flame went out, because combustion requires oxygen. Now, what happened when you tried to relight the candle? Well, you struck a match and it began to burn. However, as you moved the match towards the candle, it suddenly extinguished. Why did that happen? Remember that the carbon dioxide produced by the chemical reaction was still there, surrounding the candle. It stays there until the breezes that blow in your home eventually mix air back into the bowl. Now, as long as the match was exposed to the oxygen and air, it burned. As you lowered the match into the bowl, however, the match eventually was surrounded by only carbon dioxide. At that point, there was no longer any oxygen near the match, so combustion could not occur. Once again, at that point, the flame went out. Hopefully, then, the experiment demonstrated to you that combustion requires oxygen. This is an important point. Combustion requires oxygen. Now, let me ask you a question. Why do you need to breathe? Nearly everyone can answer that question. You need to breathe in order to get oxygen. Okay, let me ask you another question. Why do you need oxygen? The answer to that question should be a little more obvious now. Your cells need oxygen in order to burn your food for energy. Without oxygen, combustion cannot occur. Combustion is what your body uses to convert the food you eat into energy your body can use. In order for that conversion to occur, you must have oxygen. Without oxygen, you die. After all, you can be completely full of food, but if you have no oxygen with which to burn your food, you can never get energy from it. Without energy, all the systems that keep you alive simply stop. As a side note, many fire extinguishers use carbon dioxide to put out fires. Such extinguishers are best used on fires that involve flammable liquids, such as gasoline or electrical equipment. They work by simply pushing the air away from the fuel of the fire, surrounding it with carbon dioxide instead. This removes the oxygen necessary for combustion, which puts out the fire. If you have ever seen such a fire extinguisher work, it sprays what looks like a white mist at the fire. However, that's not what really happens. Carbon dioxide is a colorless gas, but as it leaves the fire extinguisher, it gets very cold. You will learn why this happens when you take physical science. Water vapor in the air condenses around this cold gas, forming droplets of liquid water and ice that make it look like a white mist is shooting out of the fire extinguisher. Okay, so you now know that combustion requires two things. First, it requires something to burn. In the case of a candle, the wax is what burns. In your cells, food is what burns. The second thing that combustion needs is oxygen. We know that combustion produces energy. After all, the flame of a candle gives off both heat and light. Those are both forms of energy. In your cells, combustion produces the energy you need to live. Does combustion produce anything else besides energy? Yes, it does. Perform the following experiment to find out the other products of combustion. What did you see in the experiments? Well, let's start with the first one. When you breathed on the mirror, it fogged up, didn't it? What made that